Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And within this module, we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within this second module, we are currently on the fourth topic, that is process system call API. So, as you know, within this topic, we are studying the operations that we would like to be able to perform on processes, right? These operations include like creation of processes, termination, waiting, right? And several miscellaneous operations also exist. So, to perform these operations, there exist system calls, right? And we are looking at the set of system calls in the Unix based operating systems that allows us to perform these important operations on the processes, right? So till now we have covered process creation, we have looked at fork and exec system calls, we have also talked about process termination using the exit system call, and in the previous video I introduced the wait system call that allows one process to wait for another process to terminate, right? So that was about wait system call, and in this video we are going to talk about a concept called as zombie and orphan processes. So there are certain processes that are known as zombie and orphan processes, and this concept is related to the working of the wait system call. So we will study this in this video, right? So let's start and see what are these processes and how they are related to the wait system call, right? Without further ado, let's get started. So let us start the discussion by recalling the flow of the wait system call. And from there, we will have we'll set the context for zombie processes, right? So, how do we have the wait system call? So, first of all, to have the wait system call, we need at least two processes, right? Because the purpose of the wait system call is that one process can wait for another process. So, let's take an example. So, here we have a process A, right? And as I said, we need at least two processes to have the wait system call, right? So, let's say this process A invokes the fork system call and creates a new process. So this is process B, which is the child of process A, right? When the fork system call is executed, we basically the operating system creates a copy of process A, which is process B, and there exists a parent-child relationship between process A and process B. Process A is the parent, process B is the child. So now we have two processes in the system, right? And let's say process A invokes the wait system call. When it does that, its execution is suspended by the operating system, right? Now the idea here is that process A has been halted, right, until its one of its child process terminates. So when process B terminates, then only process A will resume execution. That is the idea behind the wait system call. It suspends the execution of the parent process until one of its child process terminates, right? So let's now focus on process B, which is the child process. The child process can continue execution, it can do its job. Let's say it executes the exec system call to execute some other program, right? So process B is basically now executing some other program, right? When we executed fork, it was executing the same program as process A, but now it is executing some different program via this exec system call. Now, once the job of process B, that is the child process, is done, once the task that it was meant to do is done, process B, the child process, will terminate. It will call the exit system call and it will terminate, right? And when that happens, the parent process, which is process A, that will get unblocked, right? Now, the parent process, since one of its child process has terminated, it can resume execution, right? So this is the case of how the flow goes around when we have the wait system call, given that the parent goes first and calls wait before the child exits. So in this overall flow, there is a assumption that we are making that is important. The assumption that we are making here is that the parent process invokes the wait system call before the child terminates, right? So as you can see, let me go back. So we had the parent and the child. the parent has called wait before the child process terminates. So this is the normal case, right? And in this normal case, what happens is that since the parent has called wait before the child terminates, as soon as the child terminates, its exit status can be collected by the parent process, and the process control block of process B can be deallocated. We have talked about this in the previous video also, in exit also, when we were talking about the exit system call. We discussed this point that once a process terminates, all of its resources, which it has been holding, like the CPU, the memory, the IO devices, the files, all of the resources of a process are deallocated once it calls exit, except for the process control block. That process control block is kept in the system until the process A invokes the wait system call. Since in this case, process A, basically the parent process, has already invoked wait, as soon as the child terminates, its exit status will be passed on to the parent, and the parent can resume execution. There it can inspect the exit status and take appropriate action. So in this overall flow, the important thing that I want you to focus on is the order of wait and exit. If the parent process calls wait before the child exits, it's the normal case, it's the good case. As soon as the child exits, we have the exit code passed on to the parent. Now think of the other situation, right? The other situation that I want you to think about is that what if the parent does not call wait, and obviously the other part is that the child terminates. The case that we had seen just now is that the parent has already called wait and then the child exits. But what if the child exits before the parent calls wait? Let's now discuss that situation. So now let's discuss the other scenario when the child process exits before the parent calls wait, right? Let's check that scenario. So again, let's take process A, right? And let's just like we did in the previous case, process A invokes fork and creates a child process, that is process B. Right now we have two processes in the system. The parent process is process A, the child process is process B, right? And now what we will do, in the previous case, process A invoked wait before process B exits. Now we will do the opposite. Let's say process B goes on, continues execution. It calls exec system call, and this is optional, but I've just included for the sake of completeness. It calls exit system call, exec system call, and executes some other program. And once the job of process B is done, it exits. Right now, once it exits, this is the scenario that we have. The parent process has not yet called the wait system call, and the process B has exited, right? So as we discussed, the all of the resources that were held by process B, like the CPU, memory, IO devices, the files, all of those resources will be deallocated except for one thing, that is the process control block of process B, because it holds the exit code of process B, and the exit code of the child process must be passed on to the parent process, because the parent process might want to do something with it. It might want to inspect what happened to the child process that it has created and take further action. So that will only happen when process A calls wait. In this scenario, process A has not yet called wait. So we have a process in the system which has terminated. All of its resources are deallocated and it won't do anything. It's just that for this process, the PCB is kept in the system so that the exit information can be collected by the parent, right? Such a process is called a zombie process. A child process that terminates but has not been waited for becomes a zombie. So you can think of this process as something which is not doing anything, right? It is dead, but not exactly. It is almost dead. That is the definition of a zombie, right? It is almost dead. That is why we call such a process as a zombie process. In real life, in the common terminology, zombie is meant to refer to someone who is almost dead, right? So in this case, in the case of the processes that we had, this process B has terminated. It does not have any resources. It won't be doing anything. It's just that its process control block will be kept in the system because the exit information has to be passed on to the parent, and the parent has not yet called wait. That is why such a process which has exited but has not been waited upon, basically the parent has not invoked wait on the process, right, and it has terminated, such a process is called a zombie process. And let's see what happens with a zombie process once the parent invokes the wait system call. So as you can see, once process A invokes the wait system call, it will return immediately. It does not have to wait, right? Its execution will not be suspended as in the case of the previous scenario when wait was called before the process terminated. In this case, since the child process has already terminated, once parent process calls wait, it collects the exit information of the child process. The PCB for that zombie process is deallocated. It's now completely cleared. It's no more a zombie, right? And the parent process immediately returns. So if you see, once the parent process invokes the wait system call on a zombie process, its exit code is collected and the PCB is freed. So it's no longer a zombie process. It's completely dead. It's completely finished. That is why once the zombie process has been waited upon, it is cleared from the system. And in this case, the parent process does not have to suspend its execution. It can return immediately. So this was the concept of a zombie process, a process which has terminated, but wait system call has not been called upon. It is called a zombie process. For such a process, only the PCB is kept in the system. So now what we'll do, we'll quickly see how the exit code is collected for such a process, right? We'll see a zombie process and how once the how is its exit code collected, and how once the exit code has been collected, such a zombie process is cleaned from the system. We'll quickly see that. So now we'll see how the exit code of the child process, the zombie child process, is collected by the parent when it calls wait, right? So let's take the same example, right? This is process A and it creates a child process by invoking the fork system call, right? As you can see, once the fork system call is done, we have a new process, process B, which is a copy of process A. And when the fork system call returns, we now have two processes in the system. Process A is the parent of process B, whereas the B is the child of process A, right? And let's take the case when process B exits before process A, the parent process invokes wait. That is when it will become a zombie process. The process B goes on and like requests for termination by calling the exit system call, and it passes the exit code. This S integer that you see, this is the exit code of process B, and it is used to signify whether the process completed its job successfully or was there some kind of error. So that is the significance of the exit code, and it is crucial that we pass that back to the parent so that the parent can inspect that and it can take some appropriate action, right? So process B goes on, calls exit, and it will get terminated. All of its resources will be removed except for the PCB. In the PCB, the exit system call stores the exit code, right? And now this is a zombie process. So there is no process in the system, right? The child process, that is process B, has just exited. It does not, there is no process. All of its resources have been free. All we have is the process control block. It is just a data structure where all of the information is kept that is associated with the process. So that is why this is a zombie process. It's just a PCB. So we can see that the kernel maintains a minimal set of information about the zombie process. Obviously, in the process control block, what are these information? The process ID, obviously, the unique identifier of the child process, the termination status, basically this exit code, and some resource usage information in order to allow the parent process to later perform a wait and obtain all of this information about the child, right? So the whole point of the zombie process is that we'll keep some minimal amount of information in the process control block, and this process control block is the only thing that is remaining in the system. The process is gone, all of its resources are released. It's just that we have kept the process control block, right? This is like a half dead thing. It's almost dead, but the PCB is just kept so that the parent can obtain the information from the PCB. So let's see how that will be done. So once the parent invokes wait, right, this is after the child has terminated, the parent will invoke wait, and if this status integer, that this if this status is not null, if the argument to wait is not null, then we'll store this exit code into this integer. If status is not null, basically it means this is a address to a valid integer, and we'll store the exit status into this integer pointer. If it is null, then we won't do that. If it is not null, then we will store the exit code in this integer pointer, right? And once the exit code has been collected, the PCB of the zombie process will be deallocated. Now we can say that the zombie process does no longer exist and it is completely dead, right? Just before deallocating the PCB, we have a zombie process. After the PCB is also cleared, the zombie process is gone, right? And what happens next, the exit status is returned to the parent, and after wait returns, the calling process resumes execution. The PID is also returned the exit code has also been returned, and the PCB of the zombie process has been cleared. So this is how this concept of zombie process works. If a child terminates before its parent calls wait, it will be terminated. All of its resources will be released. Only its PCBs will be kept in the system as long as the parent does not call wait. In the PCB, there is some information about the exit status, and once the parent collects that, that PCB is also cleared. The zombie process in this is then completely cleared, right? So this is how all of it works, right? The exit status can be inspected by the parent to take appropriate action. So this is the whole point of the zombie process. We want to pass on the exit status to the parent because it is an important piece of information using which the parent can take important decisions as to if the child process was successful, then it would want to do something. Otherwise, it would want to do something else. So it is important that we pass the final information of the child to the parent. That is why we have this concept of zombie process, right? And I'll show you the PCB of the XB6 operating system. This is the PCB struct proc of the XB6 operating system that we have been talking about, right? In this XB6, I want you to look at these two pieces of information: the state, the process state. So you can see in the XB6 we have a zombie state, right? And this is the place where we store the exit code, int x state, exit status to be returned to parents wait, right? So right, in the XB6 operating system also you can see all of these concepts exist. We have this concept of a zombie state, and within this PCB the exit code will be saved until the parent calls wait. So this is the overall idea of the zombie process. I'll show you one more visual to make the things more clear, right? So this is process A. Let's say this is a parent process and it creates multiple child processes, right? And with each of them we have this process control blocks associated. So basically for every process we will have a process control block, right? And let's assume that all of these processes terminate before the parent process invokes wait. So all of these PCBs that you see, these are all process control blocks of zombie processes. Till a zombie is not removed from the system via a wait, it will consume a slot in the kernel process table, and if this table fills, it will not be possible to create further processes. So it could be the case that in some kernels, the process control blocks, that all of the process control blocks, they are not stored in a list, they are stored in a table, right? So there is a limit to the amount of processes, the number of processes, the total number of processes that we can have in the system if that table fills up, right? So every time we create a process, we are filling up the entry in the PCB table, right? And if we are not calling wait, then even if the process has terminated, we still have that entry, we still have the PCB. So it's very important in such systems. In some systems, the PCB, there might not be any limit to the number of processes that can exist in the system. The PCB could be stored as a linked list which can grow dynamically. But there are some systems where all the PCBs are stored in a table, and there is a cap to the number of processes that can exist in the system. Every time you create a new process, one entry will be filled up, one PCB will be taken up. And if those processes terminate, but you're not calling wait, then we have zombie processes. These processes do not exist, but we have the PCBs remaining because we have not yet called wait. So it's very important that we call the wait, and this wait system call will clear up the PCBs of zombie process, and those slots will be free so that they can be reused. So that is why it is very important that the wait system call be called upon all the zombie processes. When the parent is creating the child processes, it is necessary that it clear up the PCBs of zombie processes, right? This way, if in the system, that is in some systems, as we just said, there is a cap to the number of processes that we have since it's stored as a table, right? So this is how the overall idea works. There are child processes. Once they exit, if the parent has not called wait, all of them will become zombie. Their PCB will be kept in the system. Once the parent process invokes wait, all of those PCBs will be cleared. And as we discussed, it is very important to clear those PCBs because it can be the case that the number of processes, there's a cap to the number of processes, and we are filling up the process table entry. So on the same lines, what another question that I would like to raise is that what if the parent dies before calling wait? We have been stressing upon this fact that it is very important to call the wait on the child process. Once it terminates, it is very important for the parent process to call wait because the PCB needs to be cleared, right? Once the child has been terminated, it is a zombie process. Its PCB is lying for the exit code to be collected. But what if the parent dies before calling wait? Let's talk about this. So let's understand what happens if the parent dies before calling wait, right? In such a scenario, what we have is called a orphan process. right? A process that continues to run after its parent process has finished or terminated is called an orphan process. So, like in real life, what is an orphan? An orphan is someone whose parent has unfortunately died or passed away, right? So, the same terminology is used in the context of computer processes. If there is a process whose parent process has terminated, right, then that process, the child process, which is still executing, it is not terminated, only its parent has terminated, that child process becomes an orphan, right? So let's see what happens in that case. And we have stressed upon this point that it is important that we have a parent process which can call wait, right? Because once the child process terminates, it will become a zombie process, and there will be no parent process to call wait on the zombie process, and that PCB of the child process will be lying around. So what happens in this case? So let's take this example. Let's say we have a process A and it creates several processes, and these are the process control blocks of these children processes, right? And we are assuming that the parent process terminates. So all of these processes, all of these children processes become orphan processes, right? Right. Understand the difference between a zombie process and an orphan process. A zombie process is one which has exited, but the parent has not yet called wait. An orphan process is one where the parent process has terminated, right? In the zombie, the child process is getting terminated before the parent process calls wait. In the orphan process, the parent process is getting terminated. Now, the question here is that who will call wait on these processes once these processes exit, right? Once, if there is no parent process for them, then we will have, once these children process terminate, then they will forever be zombie processes, right? So for that, what we have in the system is that the init process, right, the root process, the first process that is created by the operating system, it basically acts as a parent. If a parent process terminates, then its children, if any, are adopted by init, right? So in this case, we saw that parent process A terminated, right, while its children processes were executing, right? And these processes, which have become orphan processes, will be adopted by the root process, the init process. Why is this mechanism? This mechanism ensures that there is always a parent process for a child process, so that when the child process terminates, when it becomes a zombie, the parent process can call wait and clear that PCB, right? So once these, so now that these processes have been adopted by the init process, they are no longer an orphan, they do have a parent process, right? And once they terminate, they'll become zombie processes. And now, since we already have the parent process as init, it will call the wait and it will clear these clear the PCBs of these zombie processes. So init calls wait periodically to remove the zombies and release the PCB of the orphans, right? So once the init calls wait, all of the zombie PCBs will be released. So how, this is how the concept of zombie and orphans work. So we discussed the case of the zombies first. The zombie processes were the ones whose where the child process terminates before the parent calls wait. In that case, there is a process which has terminated, all of its resources have been deallocated. It's just that there is a PCB lying around containing the exit code. It's almost a half dead process. That is why it is called a zombie process, and it is important to pass on the exit code of the zombie process to the parent and also to clear up that PCB, right? So that is why we have that is why it is important that the parent process call wait, and eventually when the parent process invokes wait, all of these zombie processes are cleared. Then we talked about the case when the parent process itself terminates while its children processes are executing. Then these children processes become orphan, right? And when they, if there is no one to adopt these processes, once the children processes die, there will be zombie processes lying around in the system, and they will consume of slots in the process table. So that is why there is a mechanism whereas where whenever there are orphan processes, they are adopted by the root process, that is the special process created by operating system. And when those orphan processes would die, once they would become zombie, they would be waited upon by the init process and their PCBs will be released. So this is how the concept of zombie and the orphan processes work. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.